There is a distance so small that if you tried to look at it, the universe would stop you. Not because your eyes are weak. Not because nobody has built a sharp enough microscope yet. The trouble runs deeper than that. If you tried to look that closely, the looking itself would punch a hole in space and swallow the very thing you were trying to see. That distance has a name. We call it the Planck length. And the honest truth, the part hardly anybody says out loud, is that we do not know what goes on down there. Nobody does. But the chase to find out, the way every clue turns around and bites you, that is one of the finest detective stories in all of physics. So let me lay out the clues, one at a time, and you try to solve it right along with me. First, how small are we talking? Write it down. About 1.6 times 10 to the minus 35 meters. That string of words does nothing for you, and it shouldn't, because no human being alive has a feeling for a number like that. So let me build it up. Take an atom. Most folks already think an atom is the small end of things. It isn't, not even close. Go inside the atom, past the whole cloud of electrons, all the way down to the nucleus, and pick out a single proton. A proton is about 10 to the minus 15 meters across. That alone is 100,000 times smaller than the atom around it. Now do something silly. Take that one proton and blow it up like a balloon until it is 100 kilometers wide. A ball of proton the size of a whole city, spilling past the horizon. You would think that inside something blown up that enormous you could fit just about anything. And yet, sitting in there, the Planck length would still be no bigger than one single ordinary proton. That is how far down we are going. A proton inside a city. We are not standing near the bottom of the ladder. We have fallen clean off the ladder. And it is not only a distance, there is a partner to it. A stretch of time so brief, it makes the distance look generous. About 5 times 10 to the minus 44 of a second. That is roughly how long light takes to cross a single Planck length, and light is the fastest runner there is. It is the shortest tick of time our physics can talk about without falling flat on its face. Below it, the clean ideas of before and after, of this happened and then that happened, may simply stop being clean. So we are not only hunting for the smallest place, we are hunting for the smallest moment, too. Here is the first real clue, and it is a strange one. Where did that number even come from? Did somebody measure it? No. Nobody measured it. Nobody has ever come within 1,000,000 miles of measuring it. The number was built. Near the end of the last century, a careful German fellow named Max Planck was playing with the constants of nature, not the equations, just the bare numbers that nature seems to insist on. There is the speed of light, about 186,000 miles every second, the fastest anything can travel. There is the gravitational constant, the number that tells you how strongly one lump of matter tugs on another. And there is the little quantum number, Planck's own constant, the one that says energy comes in lumps instead of in a smooth pour. Look at what each of those three is the boss of. The speed of light rules space and time and the cosmic speed limit. The gravitational constant rules gravity, how matter bends the world around it. The quantum constant rules the small, the lumps, and the fuzziness. 3 separate kingdoms, 3 separate rulers, and they have no business knowing about one another. And yet Planck noticed that if you take those 3 numbers and multiply and divide them in just the right way, the seconds and the grams and all the rest cancel away. And what you are left holding is a length. One particular length. This one. Stop and feel how odd that is. It is as if you took the price of bread, the speed of a sneeze, and the weight of your grandmother, combined them just so, and out popped the exact width of your front door. You would not shrug and say coincidence. You would say, wait a minute, why should those things conspire to hand me a door? A length built from all 3 kingdoms at once is not just any length. It is the one place where all 3 rulers must be obeyed at the same moment. No wonder it smells strange. What is hiding behind that smell has to do with two great ideas, the two crown jewels of physics, and the dirty little secret that they cannot stand each other. The first jewel is the quantum theory. It rules the small: atoms, electrons, light. Down there, the world is jumpy and fuzzy and grainy. A thing does not even have a definite place until you pin it down. The whole game is uncertainty and lumps. The second jewel is Einstein's gravity. It rules the large: stars, planets, the bending of space and time around anything heavy. And in that theory, space and time are smooth. Smooth, like a freshly pressed sheet, curving gently, with no jitter and no grain anywhere. You can see the collision coming. One jewel says smooth, the other says grainy. For almost the whole universe, the fight never breaks out, because gravity is so feeble that down among the atoms you can ignore it entirely, and out among the stars the quantum jitters are far too tiny to matter. The two jewels keep separate houses and never knock on each other's doors. Push down toward the Planck length, though, and the two houses cave in on each other. Down there, gravity is no longer feeble. Squeeze enough into a space that's small, and gravity turns into a monster. And the quantum jitters are no longer tiny. So now you are forced to use both theories at once, the smooth one and the grainy one, in the same place, at the same instant. And the moment you sit them at one table, they start screaming nonsense. You try to calculate something simple, the chance of one little thing happening, and the answer that comes back is infinity. Not a big number. Infinity. Which is nature's way of telling you that you asked your question with the wrong tools. The Planck length is, roughly, the doorway where both of our finest theories of the world stop working at the very same moment. That is why it is special. Not because we know what waits there. Because it is precisely where our knowing runs dry. Now the tidy mind wants a tidy answer, and the tidiest one people grab for is this. Maybe the Planck length is the smallest possible thing, the pixel of reality. The little square on the screen of the universe, below which there is no smaller and no in-between and nothing at all. Space made of tiny blocks, like a wall made of bricks, and the Planck length is the size of one brick. It is a lovely picture. It is clean. It is easy to draw on a chalkboard. And I have to be straight with you, because being straight is the only thing worth doing. We do not know that it is true. Nobody has ever shown that space comes in bricks. It might. That is one guess among several. But do not let the neatness of an idea trick you into thinking it has been proven. Nature is under no obligation to be tidy for our comfort. So set the pixel down on the table as a suspect. Do not let it stroll out the door as the answer. Not yet. Here the case gets really good. Because you might say, fine, Feynman, quit talking and go look. Build the microscope, take the photograph, settle the thing. So let us try. And to try, you have to understand how looking actually works. To see anything at all, you have to bounce something off it. Light, usually. Little packets of light, what we call photons. You throw light at the thing, some of it bounces back into your eye, and that bouncing is seeing. A photograph is just that, frozen. But here is the catch that every photographer half knows in his bones. To make out fine detail, you need light with a short wavelength. Long, gentle, rolling waves of light wash straight over tiny things and tell you nothing, the way a slow ocean swell rolls over a pebble without ever noticing the pebble is there. To feel something small, you need short, choppy little waves. So to see a thing as small as the Planck length, you would need light whose wavelength is that small. Fantastically, impossibly short. And short wavelength light comes with a bill attached. The shorter the wave, the more energy each packet carries. A long, lazy radio wave carries almost nothing. A short, vicious wave carries a wallop. So to sharpen your light enough to photograph the Planck length, you would have to load each single photon with a colossal amount of energy. How much? Something like the energy of a whole bolt of lightning crammed into one particle. One particle, far smaller than a speck of dust, carrying the punch of a lightning strike. And now nature springs the trap. Because Einstein showed us that energy and mass are the same thing wearing different coats. Energy is heavy. And if you concentrate that much energy into a region that small, you have packed so much mass into so little room that you have made, right there at the tip of your microscope, a black hole. A real one, born out of the very flash you were trying to see with. And a black hole does the one thing that ruins every photograph ever taken. It swallows the light. Nothing comes back out. Your picture is solid black. And do not think you can slip past this by using something other than light. Throw an electron at it. Throw anything you please. The rule does not care what you throw. To pin down a tiny spot with any probe at all, the probe must carry a short wavelength, and a short wavelength always means high energy, and high energy crammed into a tiny region always makes a black hole. There is no side door. Every probe you could ever choose marches straight into the same trap. So sit with what that means. It is not that the experiment is merely difficult. It is not a matter of a bigger budget or a cleverer lens. The harder you try to look, the bigger the black hole you make, until that black hole is itself about the size of the thing you were chasing. The looking destroys the looked at, every single time. Nature has built a lock, and the harder you shove on it, the tighter it holds shut. And do not imagine we are close to beating this by brute strength. The greatest machines we have ever built to smash particles together, our proudest and most enormous accelerators, fall short of the Planck scale by more than 1,000,000 billion times. To reach it head-on, you would need a machine beyond anything humankind has ever dared to dream. So for now, the Planck length sits behind a wall we cannot climb, cannot tunnel beneath, and cannot blast through. Every direct road is closed. So what is the answer to our mystery? What actually happens at the Planck length? I am going to give you the real answer. And for about 10 seconds it is going to sound like a letdown. And then I hope it sounds like the most thrilling thing you have heard all week. The answer is, we do not know. We genuinely, honestly do not know. There is no accepted theory that tells us. Anybody who says otherwise with a straight face and total certainty is selling you something. But we are not struck dumb. We have guesses. And they are marvelous guesses, and they cannot all be right. Let me set the main suspects in front of you. One of my own teachers liked to picture it as a kind of foam. From far off, space looks calm and smooth, like the surface of the sea seen from a high airplane, flat and serene. Drop down close, all the way to the Planck scale, and maybe that smoothness was only a lie of distance. Maybe down there space is frothing and boiling, bubbling in and out of being, churning like the ocean in a gale, with little pockets and holes flickering open and snapping shut faster than you could ever name them. A quantum foam, calm from afar, violent up close. Another camp says the smallest things are not points at all, but tiny vibrating strings, little loops of something, each one roughly the size of the Planck length, and that everything we call a particle is just one of these strings humming a different note. In that picture, the Planck length is not a brick, but the length of the fundamental fiddle string of the whole universe. And there are those who suspect that distance itself simply stops meaning anything down there. That asking what is smaller than the Planck length is like asking what lies north of the North Pole. The words line up into a sentence. The sentence has no answer. Some of them think that if you somehow managed to probe below it, space would fold back on you and hand you a larger distance instead, as though the universe flatly refuses to let the idea of smaller keep running. And there is one more possibility, the humblest of the lot. Maybe the Planck length is not the bottom at all. Maybe it is only the place where our present map runs out, the edge of what these particular theories can say, with a whole world of structure underneath it that we are simply not yet equipped to imagine. The number might be a signpost, not a wall. We have been wrong before about where the bottom lies. We once thought the atom was the bottom. We were not even close. Foam, strings, a floor where the very word distance dissolves, a signpost mistaken for a wall. These are not facts. They are honest attempts, and the people making them are nobody's fools. They are some of the finest minds we have, And right now nature has simply not told us which of them, if any, is reading her correctly. Here is what gets under my skin, what keeps me turning it over. The Planck length is a place we can point straight at. We can write its size down to several decimal places. We can tell you almost to the meter where on the great ladder of scale our entire understanding of the world gives out. We have mapped the exact street corner of our own ignorance. And then we have to stand on that corner and admit we cannot see across the road. People sometimes imagine that science is a finished thing, a thick book of answers handed down from on high. It is nothing of the sort. It is mostly this. It is standing at the edge of the map, where the known roads run out, staring into the fog, and being honest enough to write, right here we do not yet know. That is not a flaw in the work. That fog is the work. Everything we have ever figured out was once sitting on the far side of a line exactly like this one. So the next time somebody tells you we have got it all worked out, you tell them about a distance so small that looking at it makes a black hole. A distance we built out of 3 numbers that had no business ever speaking to each other. A doorway where the 2 greatest theories ever written both fall silent in the very same breath. We do not know what lies on the other side of that door. And I happen to think that is about the most thrilling sentence a human being can say out loud. If you had to place your bet tonight, with no certainty allowed anywhere, which picture would you put your money on? The foam, the strings, or the idea that smaller simply stops? And what is it that tips you toward your choice?